Most animals survive by being bigger, faster, or more aggressive. The pistol shrimp does none of those things. It is small, fragile, barely a few inches long. You could hold it in the palm of your hand and never suspect what it is capable of. And yet, this animal produces one of the loudest sounds in the entire ocean. Louder than a jet engine. Louder than most explosions. A sound so violent it creates temperatures nearly as hot as the surface of the sun. Not metaphorically, literally. For decades, scientists didn't even believe it was possible. Naval sonar operators once thought fleets of submarines were hiding underwater until they realized the noise wasn't machines at all. It was shrimp, a creature so absurdly over-engineered that it breaks the rules of biology, physics, and common sense at the same time. Nothing about the pistol shrimp is normal, and once you understand how it works, you start to realize just how thin the line is between life and destruction in the natural world. At first glance, the pistol shrimp looks unimpressive. It doesn't hunt like a shark. It doesn't poison prey like an octopus. It doesn't crush shells like a mantis shrimp. In fact, most of its body is ordinary. Small eyes, soft shell, slow movement. If evolution were a competition, the pistol shrimp looks like something that should have lost millions of years ago. But evolution doesn't reward appearances. It rewards solutions. And the pistol shrimp solution is hidden in a single oversized claw claw, so dominant that it replaces everything else. The shrimp doesn't bite, it doesn't stab, it doesn't tear, it fires. That claw is not a claw in the traditional sense. It is a biological weapon. One side is shaped like a hammer, the other like a socket. When the shrimp snaps it shut, it does not strike its prey directly. Instead, it collapses the water around it. The snap is so fast, faster than the blink of a human eye, that it creates a low-pressure vacuum bubble. And when that bubble collapses, it does something no animal should be able to do underwater. It releases a shockwave, a flash of light, and a burst of heat that can exceed 4,700 degrees Celsius. That is hotter than lava, hotter than molten steel. For a fraction of a second, the pistol shrimp creates a plasma event inside the ocean. This phenomenon is called cavitation. Engineers struggle with it. Submarine propellers are damaged by it. Industrial turbines are destroyed by it. And yet, this shrimp performs it effortlessly, repeatedly, without harming itself. The shockwave alone is enough to stun or kill small fish instantly. The sound can exceed 210 decibels, louder than a gunshot, louder than a rocket launch. Fish don't even know what hit them. They are alive one moment and unconscious the next, floating helplessly in the water. The shrimp then casually swims over and eats them. But the truly disturbing part is this. The pistol shrimp doesn't need direct contact. It kills at a distance. In the dark, cloudy, cluttered environment of coral reefs, that makes it nearly unstoppable. Visibility doesn't matter. Speed doesn't matter. Speed doesn't matter. Armor doesn't matter. If the shrimp knows where you are, it can fire. So how did something like this evolve? To understand that, you have to forget the idea that evolution is gentle or logical. The pistol shrimp didn't become a weapon overnight. Its ancestors were ordinary snapping crustaceans using small clicks and mechanical snaps to communicate or intimidate. Over millions of years, those snaps became faster, stronger, more specialized. Muscles grew larger. Joints became reinforced. The claw turned asymmetrical, one side sacrificed for power. Eventually, the snap crossed a threshold. It became fast enough to manipulate water itself. At that point, the shrimp stopped being just an animal. It became a system, a biological machine exploiting the physical limits of liquid environments. It no longer needed sharp teeth or venom. Physics became its weapon, and that weapon changed everything about how it lives. Pistol shrimp are not fast swimmers. They are not agile hunters. Many species can barely see, so instead of chasing prey, they wait. They live in burrows carved into sand or coral rubble. Some share these burrows with goby fish in one of the strangest partnerships in the ocean. The shrimp digs and maintains the tunnel. The goby stands guard. The shrimp is nearly blind, so it keeps one antenna constantly touching the goby's body. If danger approaches, the goby flicks its tail. The shrimp retreats instantly. Two species, two nervous systems, operating as one organism, not out of friendship, but out of survival. Inside that burrow, the shrimp becomes something else entirely. It is no longer prey. It is a turret. Anything that crosses the entrance without permission risks being erased by a sound it cannot outrun. Predators learn quickly. Fish remember. Reefs adapt around it. But the pistol shrimp doesn't just defend itself. It reshapes its environment. Its constant snapping contributes to one of the loudest ambient noises in shallow tropical seas. In some regions, entire reef systems crackle non-stop with shrimp fire. The ocean there never goes silent. During World War II, this noise confused sonar systems, masking submarines and warships. Human technology, designed at enormous cost, was outperformed by crustaceans smaller than a finger, and yet, despite all this power, the shrimp remains vulnerable. Its claw takes time to regenerate if lost. The snap requires precise muscle timing. A damaged joint means death. Evolution didn't make it invincible, it made it extreme. And extremes come with costs. What makes the pistol shrimp truly unsettling is not just what it does, but how casually it does it. There's no struggle, no chase, no visible violence. Just a click, a flash, and then stillness. In a world where most predators rely on speed, teeth, or poison, the pistol shrimp relies on an invisible event that happens faster than perception. Its prey never understands what killed it. And that raises a deeper question. If something this small can weaponize physics to this degree, what else in the natural world is hiding capabilities we've barely begun to notice? This is not the story of a shrimp. It is the story of how evolution doesn't care about fairness, only effectiveness. And this is just the beginning. The physics that shouldn't exist in why. Engineers study this shrimp for a long time. Scientists didn't believe what they were seeing. Not because the data was unclear, but because the implications were absurd. Water, by nature, resists compression. It absorbs force. It slows explosions. That's why underwater detonations behave differently than explosions in air. And yet, the pistol shrimp was somehow generating shockwaves, light, and extreme heat underwater using nothing but muscle and timing. No fuel, no electricity, no chemical reaction. Just motion. When researchers finally captured the snap using high-speed cameras, what they saw forced a rewrite of assumptions about what small biological systems could do. The claw doesn't close like a simple hinge. It rotates, locking into place with a latching mechanism that stores energy the way a crossbow does. Muscles load tension slowly, and then, when the latch releases, the claw accelerates faster than almost any known biological movement. The tip of the claw reaches speeds exceeding 30 meters per second, displacing water so violently that pressure drops instantly, forming a cavitation bubble. This is the same destructive phenomenon that damages ship propellers and industrial turbines. Engineers spend millions trying to prevent it. The shrimp triggers it deliberately. The bubble itself is not the weapon. It is what happens next that defies intuition. The surrounding water rushes in to fill the low-pressure void, and when it collapses, the implosion releases a microburst of energy. For a few microseconds, temperatures inside that collapsing bubble spike to thousands of degrees. Sensors detect a brief flash of light, a phenomenon known as sonoluminescence. This means the shrimp is not just stunning prey with sound. It is briefly generating plasma inside the ocean. With a claw. No vertebrate, no insect, no mammal does anything remotely comparable. The shrimp is exploiting a loophole in physics using water itself as a medium to amplify force beyond what muscle alone should allow. This discovery didn't stay confined to marine biology. Physicists took notice. Engineers took notice. Military researchers took notice, because if a shrimp can do this repeatedly without damaging itself, then nature has solved a problem humans still struggle with: how to generate controlled, repeatable, high-energy events at microscopic scales. Submarine designers study snapping shrimp noise because it interferes with sonar. Medical researchers study cavitation because controlled bubble collapse can be used to break kidney stones or target cancer cells without invasive surgery. fluid dynamicists model shrimp snaps to understand erosion, turbulence, and shock propagation. The pistol shrimp is no longer just an animal, it is a case study in applied physics. But the more scientists learn, the stranger the implications became. The shrimp's claw doesn't just fire once, it can fire again and again hundreds of times a day. Each snap produces forces that would tear apart most mechanical systems of comparable size. Yet the shrimp's joint survives. The exoskeleton doesn't fracture. The muscles don't rupture. Microscopic analysis revealed reinforced structures at stress points, layered materials that dissipate energy, and flexible regions that absorb shock. Evolution didn't just create a weapon, it created a recoil management system. Every snap is balanced, every vibration redirected. This isn't brute force. It's precision engineering refined over millions of years. And then there's the sound. To human ears underwater, the snap is deafening. But to fish and invertebrates, it is catastrophic. Sound travels faster and farther in water than in air. A snap can propagate through complex reef structures, bouncing, refracting, and overlapping with others. In dense shrimp populations, the combined noise forms a constant acoustic fog. Predators that rely on sound are disoriented. Prey can't distinguish threats. Even large animals avoid areas where snapping shrimp dominate. In effect, the shrimp creates an invisible force field, not through territory or aggression, but through noise pollution generated by biology itself. This leads to an uncomfortable realization. We often think of humans as the only species capable of altering environments at scale, but pistol shrimp reshape entire soundscapes. They influence which species settle where. They change predator-prey dynamics without ever moving far from their burrows. In some shallow seas, snapping shrimp are the loudest animals present, outcompeting whales, dolphins, and ships. An animal you could crush under your shoe controls the acoustic character of kilometers of ocean. Yet, despite all this power, the pistol shrimp remains deeply constrained by trade-offs. Its oversized claw comes at a cost. It grows slowly. If lost in a fight or accident, it takes weeks to regenerate. During that time, the shrimp is defenseless. Some species even switch handedness, regrowing the dominant claw on the opposite side while the original shrinks. This plasticity is remarkable, but it reveals how precarious the shrimp's strategy is. Lose the claw, lose everything. Evolution didn't give it backup weapons. It went all in. And then there is the question of perception. The shrimp doesn't understand physics. It doesn't know what cavitation is. It doesn't aim in a conscious sense. It relies on instinctive timing and proximity. This makes its success even more unsettling. Complex outcomes don't require complex minds. They require systems tuned by selection pressure. Over time, small advantages accumulate. A slightly faster snap, a slightly stronger joint, a slightly better latch. Millions of generations later, you get an organism that can generate plasma without ever knowing what plasma is. This challenges how we think about intelligence and power in nature. We tend to associate extreme capabilities with large brains, complex behavior, or social structures. The pistol shrimp has none of those. It doesn't plan. It doesn't strategize. It executes perfectly, every time. In a sense, it is evolution distilled, no excess, no flexibility, no mercy. A single solution optimized to the edge of physical possibility. Engineers trying to replicate this system face a paradox. They can build machines that snap fast, or generate bubbles, or create shockwaves, but not all three at once, not repeatedly, and not at this scale. Materials fatigue. Components erode. Systems fail. The shrimp doesn't. Its claw is self-healing. Its muscles repair. Its exoskeleton molts and renews. Biology sidesteps problems by rebuilding itself continuously. Machines cannot do that. Not yet. And that brings us to the deeper reason the pistol shrimp unsettles scientists. It suggests that the limits we assume about size, energy, and capability are often artificial. Nature doesn't follow our engineering rules. It finds paths we didn't consider. If a shrimp can weaponize cavitation, what other physical phenomena are being exploited quietly by organisms we overlook? What else is happening at scales too small, too fast, or too subtle for us to notice. The pistol shrimp forces a shift in perspective. It's not just a curiosity. It's proof that the natural world still outpaces our understanding. That evolution can arrive at solutions so counterintuitive they look impossible until you slow time down enough to see them. And once you do, you're left with a humbling thought. If this exists in shallow water, in plain sight, studied for decades, what else is waiting in the dark? Because the shrimp's story doesn't end with physics. It ends with consequences. And those consequences ripple outward into ecosystems, into human technology, and into questions we don't yet know how to ask. How a small animal rewrites ecosystems, outsmarts predators, and breaks the meaning of size is supposed to matter in nature. Bigger animals dominate. Heavier jaws win. Faster muscles decide outcomes. That logic works on land, where mass and leverage rule. Underwater, the rules are different, and the pistol shrimp exploits that difference with ruthless efficiency. It doesn't compete on size because it doesn't have to. Instead, it alters the environment in ways that make size irrelevant. Entire reef ecosystems reorganize around the presence of snapping shrimp, not because the shrimp actively controls them, but because its behavior changes what is safe, what is audible, and what is possible. In shallow tropical waters, the constant crackle of shrimp snaps forms a living acoustic fog. To predators that hunt by sound, this noise is disorienting. Direction becomes ambiguous, distance becomes unreliable. For prey species, the fog is a warning. Danger exists here, even if you can't see it. Over time, fish learn to avoid certain burrows, certain rubble fields, certain patches of sand, not because of a visible threat, but because of an invisible one that announces itself with sound. This is ecological influence without movement, dominance without pursuit, control without confrontation. The shrimp's burrow becomes the center of a micro-territory. It digs relentlessly, clearing sediment, moving shells, reshaping the seafloor grain by grain. These burrows provide shelter not just for the shrimp, but for other organisms that can tolerate its presence. Worms, small crustaceans, and microorganisms colonize the tunnels. The sediment chemistry changes. Oxygen flows differently. Nutrients concentrate. A single shrimp, through repetition alone, engineers a tiny habitat that didn't exist before. Multiply that by thousands across a reef, and you get structural change at scale. Coral rubble stabilizes. Sand shifts slow. New niches appear. The shrimp is not a passive resident. It is an unintentional architect. And then there is the alliance that should not work, but does. The partnership between pistol shrimp and goby fish looks simple on the surface. One digs, one watches. But beneath that simplicity is a deeply integrated system of trust enforced by survival pressure. The shrimp is nearly blind. The goby has excellent vision, but no digging ability. Alone, both are vulnerable. Together, they become resilient. The shrimp maintains the burrow with obsessive care, constantly reinforcing walls, clearing debris, expanding chambers. The goby hovers at the entrance, eyes scanning in all directions. Physical contact is constant. One antenna on the goby's flank is enough. A flick of the tail sends a signal. The shrimp retreats instantly, abandoning food if necessary. There is no hesitation, no verification. In evolutionary terms, that level of trust is extraordinary. It means the cost of ignoring the signal is always higher than the cost of obeying it. Over time, that equation locked the partnership in place. What's unsettling is how little intelligence is required. There's no planning, no negotiation, no awareness of cooperation as a concept. The system works because it must. Natural selection doesn't care about intent. It cares about outcomes. And the outcome here is mutual survival through specialization taken to extremes. One organism outsourced vision, the other outsourced excavation. Together, they outperform competitors that try to do everything themselves. This is not friendship, it is optimization. Predators learn quickly that the shrimp is a bad target. Fish that attempt to invade a burrow are often stunned before they can retreat. The snap doesn't need to kill. A moment of disorientation is enough. In a reef environment full of sharp coral and other predators, a stunned fish rarely recovers. Even animals too large to be killed outright avoid close approaches. Over time, selective pressure favors those that recognize the sound and stay away. The shrimp doesn't chase enemies, it teaches them. And once learned, that lesson persists across lifetimes through behavior and instinct. This creates a strange imbalance. The shrimp is physically weak, it could be crushed easily if caught. But it is rarely caught. Its defense is proactive, not reactive. By the time a predator considers attacking, the cost-benefit calculation has already shifted. Risk outweighs reward. The shrimp wins without fighting. This is a recurring theme in nature's most successful designs. Avoid the contest entirely. There is also a darker side to this influence. In areas where snapping shrimp populations explode, the constant noise can interfere with the communication of other species. Fish that rely on sound to find mates or coordinate movement struggle. Larval fish navigating reefs may become disoriented. Human-made noise pollution often gets blamed for acoustic disruption, and rightly so, but biological noise can be just as transformative. The shrimp doesn't intend harm, but intent is irrelevant. Impact is what matters. Ecosystems are shaped by cumulative effects, not morality. The illusion of small collapses here. We tend to rank animals by mass, height, or strength. But the pistol shrimp operates on a different axis. It converts time into power. By compressing an action into a fraction of a millisecond, it achieves effects disproportionate to its size. This is a lesson physics teaches repeatedly. Speed can substitute for mass, and precision can substitute for force. Nature learned that lesson long before humans did. What makes this especially unsettling is how common the shrimp is. This is not a rare anomaly hiding in the abyss. Snapping shrimp are everywhere in warm coastal waters. They live alongside us, beneath docks near beaches, around coral reefs visited by tourists every day. Their constant snapping forms the background noise of tropical seas. Most people hear it and never question it. The sound becomes ambiance. White noise, something ignorable, but that sound is a weapon firing thousands of times an hour, maintaining invisible boundaries, enforcing rules we don't see. And that raises a more uncomfortable thought. How many other background phenomena in nature are active processes we've simply normalized? How much power is hidden in repetition, in scale, in behaviors that seem insignificant until viewed collectively? The pistol shrimp doesn't need to be rare or dramatic. It succeeds because it is consistent, because it snaps again and again and again, turning an improbable trick into a reliable strategy. In the end, the shrimp's story isn't about sound or claws or physics alone. It's about perspective, about how easily we underestimate systems that don't fit our expectations. We expect danger to be large, visible, and aggressive. The pistol shrimp is none of those things. It is small, hidden, and methodical. And that combination, more than raw strength, is what allows it to persist, reshape its world, and quietly dominate spaces far larger than itself. If a creature this unassuming can bend physics, rewrite ecological rules, and influence environments through nothing but timing and repetition, then our hierarchy of nature is deeply flawed. Power does not always announce itself. Sometimes it clicks. The cost of extremes, regeneration, failure, and life on a knife's edge. Extreme specialization always comes with a price, and the pistol shrimp pays it every day it survives. Evolution pushed this animal toward a single overwhelming advantage, but in doing so, it stripped away safety nets that most creatures rely on. The oversized snapping claw is not just a weapon, it is a liability. It consumes energy to maintain, time to regenerate, and structural compromises that make the shrimp fragile in ways that aren't immediately visible. If that claw is damaged, lost, or misfired, the shrimp doesn't become weaker, it becomes helpless. There is no backup strategy, no secondary defense, no venomous sting or crushing jaw waiting in reserve. Everything hinges on a single joint, a single latch, a single explosive movement executed flawlessly. Claw loss is not hypothetical. It happens often. Territorial disputes, predator encounters, cave-ins inside burrows, any of these can sever or disable the snapping appendage. When that happens, the shrimp doesn't die instantly. Instead, it enters a dangerous waiting period where survival depends on time. Remarkably, many pistol shrimp species can regenerate the lost claw. Even more remarkably, If the dominant snapping claw is lost, the smaller claw on the opposite side can begin transforming into a new weapon. Muscle mass increases. The joint structure remodels. The original snapping side shrinks. The shrimp effectively switches hands. But regeneration is slow. It requires multiple molts. During that process, the shrimp cannot fire. It cannot defend its burrow. It cannot hunt efficiently. It becomes prey in a world that remembers what the snap sounds like and knows to strike when it goes silent. Molting itself is another risk. Like all crustaceans, pistol shrimp must shed their exoskeleton to grow. During molting, the body softens. Muscles detach temporarily. Movement becomes sluggish. For a snapping shrimp, this is a nightmare scenario. The claw mechanism is offline. The latch cannot function properly. The shrimp often seals itself deep inside its burrow, blocking entrances with rubble and waiting in darkness until the shell hardens again. If a predator breaches that barrier at the wrong moment, the outcome is final. Extreme power buys dominance only when it is active. During downtime, it invites catastrophe. Even when fully armed, the snap itself is not without cost. The mechanical stresses involved are enormous. Over time, microfractures can form in the claw. Wear accumulates. Evolution compensated by reinforcing critical regions and allowing periodic replacement through molting, but nothing lasts forever. This is not a system designed for longevity. It is designed for efficiency. The shrimp trades durability for performance, trusting regeneration to reset the clock before failure becomes fatal. It is a gamble repeated across millions of generations, and it works just often enough to persist. There is also the question of energy. Producing snaps repeatedly requires fuel. Muscles must reload. Tension must build. In environments where food is scarce or competition is intense, the shrimp cannot afford to fire indiscriminately. Every snap is a calculated expense. Miss too often, and starvation follows. This introduces a subtle form of restraint into an otherwise overwhelming weapon. The shrimp is not reckless. It fires when probability favors success. Evolution shaped not just the weapon, but the behavior surrounding it, tuning risk and reward until waste became too costly. The shrimp's dependence on burrows further narrows its margin for error. Collapse of a tunnel can trap it. Flooding can displace it. Reef disturbances, natural or human-caused, can erase shelter entirely. Unlike mobile predators that can relocate quickly, the pistol shrimp is rooted. Its power is stationary. Remove the environment that supports it, and the advantage dissolves. This fragility becomes more pronounced as coastal ecosystems change. Sediment shifts, coral degradation, and noise pollution alter the conditions the shrimp evolved for. A system balanced on precision does not adapt easily to chaos. What's unsettling is how familiar this pattern is. Extreme optimization produces extraordinary results, but only within narrow parameters. Outside those parameters, failure is sudden and absolute. The pistol shrimp embodies this principle in biological form. It thrives not because it is adaptable, but because its niche remains stable enough for specialization to pay off. When stability disappears, so does its advantage. And yet, despite these risks, snapping shrimp have persisted for millions of years. They survived mass extinctions, climate shifts, reef collapses, and recoveries. How? By occupying a role few others can challenge. Their vulnerability is offset by deterrence. Predators don't test them often. Competitors give them space. Their failures are catastrophic but rare enough that success dominates the evolutionary ledger. This tension between overwhelming power and total dependence defines the shrimp's existence. It lives fast, specialized, and exposed. There is no middle ground. It cannot downshift into a safer mode. It snaps, or it waits, hoping nothing notices the silence. In that sense, the pistol shrimp is a warning written in biology. Extreme solutions solve extreme problems, but they narrow the path forward. They leave no room for error. And that brings the story to its final question. If nature can push an organism this far right to the edge of physics, right to the brink of failure, what does that say about the limits we assume still exist? Because the pistol shrimp didn't just find a loophole, it lives inside it. What this shrimp reveals about evolution, power, and the rules we keep getting wrong. The pistol shrimp doesn't just challenge what we know about animals. It challenges how we think about power itself. We are conditioned to look for dominance in size, intelligence, coordination, or complexity. Big predators, social hunters, long lifespans, tool use. But the shrimp ignores all of that. It does not outthink its environment. It does not overpower it. It exploits it. It turns a basic property of water pressure into a weapon so precise that even modern engineering struggles to replicate it. This forces an uncomfortable conclusion. Many of the limits we assume in biology are not real limits at all. They are limits of imagination. Evolution does not aim for balance. It does not care about redundancy, safety margins, or fairness. It pushes systems until they work, and then keeps pushing until they almost break. The pistol shrimp is the result of that pressure. A creature optimized so narrowly that it sits at the boundary between success and failure, operating in a space where physics itself becomes part of anatomy. Its claw is not just bone and muscle. It is a timing device, a pressure valve, a trigger that turns fluid into force. When we say the shrimp fires, we are not using metaphor. It executes an event brief, violent, and final that exists only because evolution found a way to compress motion into almost no time at all. What's striking is how invisible this power is. To the untrained eye, a reef looks peaceful. Colorful fish drift by, coral branches sway, and beneath that calm surface, thousands of micro-explosions occur every hour, enforcing boundaries, reshaping behavior, maintaining order. The shrimp doesn't announce itself as a ruler, it doesn't patrol territory. It simply snaps, and the ecosystem responds. This is influence without authority, dominance without pursuit. It is a reminder that control in nature often comes from consistency, not spectacle. There is a lesson here that extends beyond marine biology. Humans tend to value adaptability, flexibility, and general intelligence as the highest evolutionary achievements. And in many contexts, they are. But the pistol shrimp represents a different path one, where extreme specialization outcompetes versatility, where a single perfected solution outperforms a dozen mediocre ones. It survives not by doing many things well, but by doing one thing impossibly well. That strategy is dangerous, it is brittle, and yet in the right conditions, it is unbeatable. This reframes how we interpret evolutionary success. Survival is not always about resilience to change. Sometimes it's about exploiting stability so efficiently that change becomes irrelevant until it isn't. The shrimp's existence is a reminder that life doesn't hedge its bets the way we expect. It places them boldly, even recklessly, trusting that the environment will hold long enough for the strategy to pay off. And remarkably often it does. There's also a humbling implication for human innovation. We pride ourselves on mastering physics, on understanding forces, materials, and energy. But here's a creature with no brain to speak of, no awareness of theory, no ability to plan beyond instinct performing feats that still surprise us. It didn't invent these mechanisms, it inherited them. Layer by layer, generation by generation, shaped by pressure we cannot replicate in laboratories. The shrimp is not smart. The process that made it is ruthless. Perhaps that is the most unsettling realization. Intelligence is not required to reach the edge of possibility. Selection is enough. Given time, constraints, and consequences, systems evolve that look designed, engineered, even intentional, without ever being guided by intent. The pistol shrimp feels like a machine because evolution treats bodies as prototypes, discarding failures and refining successes until only the extreme remains. And so the shrimp leaves us with a quiet challenge. If something so small can bend physical laws into a weapon, how many other organisms are doing things we haven't noticed yet? How many background noises, overlooked behaviors, and mundane adaptations hide mechanisms that would rewrite our understanding if we paid closer attention? The natural world is not just stranger than we imagine. It is stranger than we are prepared to accept. The pistol shrimp doesn't roar. It doesn't chase. It doesn't threaten. It clicks. And in that click is heat, light, force, and a reminder that nature's most powerful tools are often the ones we dismiss first. If you want to keep uncovering the hidden mechanisms that shape our world quietly, invisibly, and far beyond what seems possible, then stay here. There are countless systems like this waiting just beneath the surface. The natural world is full of systems we ignore. If you don't want to miss them, subscribe.